Hello, thank you for joining our session today. My name is Lenny Shaver. I'm the product director for thermal imaging and fiber optic temperature sensors at Advanced Energy. In this session, we'll be talking about some of the challenges of improving process control for furnaces such as reheat and annealing furnaces, and some of the technologies applied to improve the process control. Just a brief overview of what we'll cover in this session. We'll do an intro about industry challenges, overview of thermal techniques used to monitor furnaces, and then some details about thermal imaging as applied to furnaces, and finally, a case study.
Like it or not, we are in a never-ending quest to do more with less. Our customers are requiring that the quality be improved, performance, and the tracing and auditability of the product to make sure it meets specifications. But we can't do this by adding costs. We can't hire a bunch of metallurgists to monitor over everything. And so one solution that customers are turning to is to automate and to use sensors and systems to prove and improve the process quality. Of course, the overall purpose of a furnace is to heat something up, whether to preheat it or heat it to a process temperature. This is obviously the function of a furnace. And you're all familiar with the cliche phrase, you cannot improve what you do not measure. So measuring the temperature in the furnace and improving that temperature measurement is one way to meet many of the challenges in terms of productivity, quality, efficiency that are expected and demanded of your operations. You know, the old method of kind of an egg timer technique where you develop a recipe and have a time for that recipe and follow that in your process control does not accommodate for the variations that exist for many processes. And to improve this, to make sure that you're not wasting time or resources, the improvement of process monitoring and measurement is critical to allow you and your operation to improve either efficiency or product quality or all the above. So whether your aim is improving quality or efficiency or to have an early warning and detection of potential problems, the very first step to getting better visibility into your process is to have better data, better sensors at the front end to see either more quickly, more accurately, or monitoring more points within your system and process. And this collection of data, once you have it, often so many times we found users who've discovered things that they didn't anticipate discovering, but they invested for one purpose, and that was clear, and that pays off. But then they're paid dividends in other areas as well. So the importance of getting that front end data so that you have visibility in your process is absolutely critical. And the new technologies available make that much easier to gather that data. Of course, having the better data and better visibility, better sensors that are showing the process control, that is the first step, but not the last step, certainly not to realizing improvements in your process. So for those next steps, we've got to be able to record all that data, have tools to analyze it, and this analysis will be done by the technical team. This could be, of course, process control people, operators, metallurgists, maybe even customers in some cases. And this study of the data is where we can learn to improvements in the process and maybe what actions to take. But what's also critically important is that we can't tie up this technical staff on an ongoing basis. They cannot be, massaging and tuning each batch like it's a snowflake. This has to be automated. This has to be a learning process for the batch, and then we have to implement the improvements to realize the gains on an ongoing basis. To implement long-term process improvement gains, really needs to be automated. So with the better input data and then the analysis from the technical team, the final step is to automate this. And with that, we can improve the process control, we can capture data and quality metrics to share with our internal team, but as well as with customers who demand to see that. And we can get an ongoing improvement captured, and either that be in money savings, efficiency, capacity, and set up as well process control limits so that if the process were to drift or go outside of bounds of what's expected, to get automated alerts or alarms so that we know, hey, something may be shifted, something changed. Let's go back and again get the technical team to look at the data again to see if there is something that needs to be addressed. The chart on this slide provides a high-level comparison of common sensors used in furnaces and other industrial processes. We have in here thermocouples, RTDs, and then pyrometers and thermal imagers. All these sensors are appropriate and they all should be used or all can be used, and it's a matter of selecting the right sensor for the right job. In the case of the thermocouples and RTDs, these are contact sensors. So to be really accurate, they have to be in touch or in contact with the object they're being measured. Whereas pyrometers and thermal imagers, what's great about them is that they're non-contact methodologies. They measure the infrared radiation coming from the object or the target, and then convert that to a temperature. The thermocouples and RTs, especially for high temperature furnaces, they're limited in that they're a point contact. You can't put them everywhere, or not in a cost-effective way. And especially for higher temperature processes, they're quite prone to failure and drift over time and just surviving in the environment. So they're certainly appropriate for low value applications or maybe a couple points in a very challenging application as kind of a reference. Pyrometers and thermal imagers, these have a much faster response time. They're great for a lot of industrial processes where you're moving different batches or different work pieces through the process because they don't have to touch the object, but they do measure the object itself, the real thing that matters in the process. You're not measuring the temperature of the furnace or the flue gas in the furnace, but they're measuring the workpiece. The pyrometers measure a single point on the workpiece, and you can put multiple pyrometers into a process if you want to kind of get a gradient or see across multiple parts. But then the thermal imager, the big advantage there is it can see gradients of within a part, and it also can measure multiple parts or multiple things within the furnace simultaneously. Now, obviously, for that, it's a bit more expensive, but this is what makes it very useful for your higher value products, your higher quality products, and it can give insight both into the part temperatures, but as well as the process temperature simultaneously. So it can be used for process control of the parts and workpieces, as well as gaining insight into the overall process. There's a number of different sensors that we've talked about in the previous slide. And so this slide talks about some considerations or questions that you want to ask as you're considering upgrades or improvements or investments. And I won't talk about all of these, but I'll kind of highlight a few and you can read through all of them. The top one here talks about just how many parts and the value of the parts, right? If it's a batch process where you got multiple parts going through in a single batch, then you really to see part to part quality, you need to measure each part. So that might mean you need more sensors, more pyrometers, or thermal imaging maybe, which can measure all the parts simultaneously but distinctly. The other, of course, important thing about the parts is the value. Do you need to report distinct temperature values for each part to sort of verify its process attributes that's been through to either your own internal QA reporting or even to reports that go to end users? These requirements will drive you towards a better sensor and a thermal imager. The other one I'll kind of maybe talk about here for a moment is at the bottom, like how does this data from the sensor get collected or into your QA process or into your DCS or into your PLC? There's different ways to interface. Sometimes some controllers will have a direct input for thermocouples. In other cases, you may really want to capture this data as part of a larger data system, and maybe you're using Modbus or analogs or relays and so forth. So how the entire system is going to be connected is an important consideration, and how frequently you want to get the data. Is it something that you need to measure very quickly, or is this a process that's taking place over 18 hours? These are all the considerations for different types of sensors and what type of investment makes most sense. And of course, at the end here, finally, what's your return on investment? So obviously, this is going to be a cost in these cases, but there's going to be process improvement. So looking at both sides of that, so you can explain to management, to your customers, what investments are needed and how this will pay back to the company. Infrared cameras that are designed specifically for integration into furnaces are available that are very proven now to provide excellent data for the entire furnace or for many parts inside the furnace. These infrared cameras have a few features that make them reliable and for continuous 24/7 operation inside very high temperature furnaces. Key features include filtering that makes sure that the camera is measuring the parts or the refractory in the furnace and not measuring the flame for a gas fire type furnace. So this filtering makes sure that you don't have influence from the radiation that comes from the combustion process, but instead are measuring the infrared radiation from the parts under treatment. Another important feature is the borescope optics. These are the long optics that allow the camera to get a small hole into the furnace and give a wide view internally, but the electronics from the camera are safely on the exterior of the furnace, and this is what enables continuous operation with low maintenance for many years. A third area of features is, of course, a lot of things about the software. There's a lot of improvements continuously in the software space, but this is really critical for the automation of these systems, as well as for the initial data analysis. But software can do things like detect parts, count parts, know that the beams or parts are in the proper position, and ultimately get temperatures for individual parts if that's needed. And that is what really enables some of the advantages like exact tracking of part temperature. So if you know that a batch and a part have been treated exactly as prescribed, that they got to the temperatures, when they achieved those temperatures, and how long they were dwelled at that temperature, for example. So that can all be gathered in the software and created in a report that can be used for your metallurgy. In addition to the part tracking, there's a lot of tuning of the furnace that can be done with making sure there's uniformity or minimizing the imbalance that may exist in some furnaces. All these things combine together to kind of create advantages depending upon the type of furnace in throughput, uniformity, quality, and accuracy. Just to give a little further detail on the borescope lens, this is a critical feature for any infrared imager to be integrated into a furnace. The borescope lens really allows that camera system to be put onto a furnace and operate continuously and reliably with very low maintenance for many years. The borescope lens itself is the optical part. It has a diameter maybe roughly about 2 inches typically, and the lengths can vary, but is listed here, anywhere from 2 to 3 feet length. So this is a long length to reach through the furnace wall through a relatively small hole. Now this lens, it does have cooling and purge with it. So the purge just keeps the tip of the lens clean, just to avoid dust or deposits. And then the cooling can be either air or water cooled, and this keeps it from overheating the optical parts inside. These systems are quite mature now, and then in addition, we'll talk about some features that are monitoring that cooling, that if there's any interruption, it'll automatically retract the camera. But the lens is the part that goes into the furnace and the only part. And in addition, it can be some different treatments at the tip. So depending upon how the camera system comes into the furnace, it can kind of have a straight view, or there can be an angled optics at the tip to kind of look down or to the right or left. And that kind of depends on just the overall structure of the furnace and where it's convenient to mount and, and what the best view is of the workpieces inside. These infrared cameras for furnaces are available with two different use cases. One is a mobile type system, and the second is a fixed system. The fixed systems are what we've kind of referred to mainly for process control. These are mounted and designed with cooling and the fixtures I talked about and the features to operate 24/7 continuously in the furnace. And these are really used for automation and process optimization. The mobile cameras are used for troubleshooting and maybe to try the technology out. These are similar in terms of the optics and the infrared capabilities, but are coupled with battery systems and a radiation shield so that the operators can put them into ports and take measurements on a temporary or short-term basis, maybe a couple minutes to kind of check on work pieces or to check the process. So you can see the picture in the upper left there. This is kind of a typical case where a port door is open and someone is using a mobile camera to inspect a furnace or to check on workpieces. Whereas the picture on the right, this shows a fixed installation where the camera is installed for 24/7 continuous process monitoring. A really important feature of a continuous monitored system is that to protect the investment, if there's any interruption in the cooling facilities, that there's a system that automatically removes the camera or retracts it from the furnace. And you can see an example of that in this photo. The camera rides on a mechanism that is pneumatically operated. And so if all the cooling and power and everything is as it should be, the camera is installed in the furnace and correctly monitoring the process and outputting temperatures and doing the automation and optimization. However, if there's any interruption, for example, in the water pressure or in the air supply to the system, which is critical to the cooling and the safe operation, then there's controls that automatically detect that and that retract the camera. And of course, you can get an alarm to your system so that the operators are aware, and then they can take any actions as necessary to do maintenance or to make sure the cooling is corrected and then get back into process control and process monitoring. There's some basic hardware that is included and part of the overall system to make sure that when cameras are installed for 24/7 operation, that they have the facilities to cool and operate correctly. And this slide here shows those examples. So the core camera and the main technology is the camera and lens. That's shown on the left. But on the right-hand side here is kind of the basic accessories that facilitate the operation. Item A there shown is the main retraction system that we just spoke about. This is what the camera mounts to and slides in and out of the furnace, and that gets mounted to the furnace. And then the other items around that, that's just the cooling facilities and the controls that monitor all the air pressures or water pressures and so forth. So those all work in concert together to ensure that everything is operating and getting the proper cooling and it's safe and reliable. With all this together, it's all mature. These have enabled infrared cameras to run for many, many years at very high temperatures with very reliable performance and accurate measurement to process control. On this slide, you can see some pictures of an actual installation of an infrared camera onto a furnace. And this is two pictures of the same installation, just from different perspectives. And one thing interesting about this is you can see that the camera is actually mounted looking almost straight up. And that kind of raises another important point that the camera and its mounting to the furnace can be really in any orientation as long as the system mechanically is designed right. And this system is where it can take the weight and hold the camera in the up position or retract it down. But the mounting of the camera to the furnace, this is an important thing to consider when you're evaluating this technology. You know, where can I put the infrared camera to get the best view of the product inside the furnace. So that's usually the first consideration. And then secondarily, you'll think about just practical things such as space outside the furnace. You're going to need 6 feet at least of space just for the camera system to kind of move and retract and just to install and work on it. You also want to consider where people need to walk around the furnace. And finally, just what the temperatures are around the furnace. On the top of the furnace, some furnaces can be very hot on top, so that's kind of a consideration for the controls that are monitoring the retract and the other sensors. So all these are somewhat considerations, and you can see one other thing in this photo, which I haven't mentioned earlier, which is the air system that feeds the camera. So there is often cooling air on the pneumatics that operate the retract, and a purge air for the lens. So especially for the air that's purging the lens, it's critical that this air be clean air because it's going through the optics and we don't want to get oil or moisture onto the optics. So on the picture on the left, you can see in the lower right just the air filter and some of the regulators there that are bringing in the air, regulating it to the appropriate pressures, and just making sure that it's filtered before it goes through the lens system. Finally, just with the green light there, again on the same picture on the left, you can see that's the control box. So that houses the controller for the whole system, as well as where the sensors that are monitoring pressure and air feed into that. And conversely, the power is brought into that box, and then that powers all the accessories in the camera. One of the highest value aspects that these systems have enabled for furnace operators is to generate exact reports showing how parts were treated for temperature. This is to ensure that by part and by batch that the company can report to their end users or their own internal quality processes that they've got an accurate, traceable record of how those parts were treated. And part of all that coordination to make sure those reports are generated in an automated way without a lot of personnel involved for each batch is to automate this in software. So having the software from the camera system, which is shown here kind of with the screenshot, interfacing with the plant control system. And here that interface is shown through the OPC server block diagram there. So that's one way that it can be done. There's other ways that are supported and other methods. It can be done via Modbus, can be done via other protocols. But OPC is one of the common ones, and I'll talk about that a little bit later. But in this case, between the systems, they can keep track so they know which batch is being processed, which values that batch should be processed at. And then the camera software can measure those parts, know which parts are being measured, maybe set up different thresholds and measurement points depending upon the batch or the parts being processed. And then, of course, as the process, knowing when the process starts, logging temperatures, averages, or tracing the exact process chart. So how it ramps up and when it reaches dwell time or process temperature and so forth. So all of these can be coordinated as in software, and there's kind of common platforms to do this. So this is where working with the automation team and process team, these really critical accurate temperatures can be fully automated so that on an ongoing basis to each batch process, there's a recorded, clear, accurate log of how parts were treated in that batch. And this slide just gives a little bit further detail on some of the things that are commonly done in software. And I'm not going to go into all of this, but within the software, of course, the critical part is measuring the part temperature. And this can be, done in either max, min, average. There can be standard deviations and all kinds of different statistical analytics that the thermal imaging camera software can measure and calculate for the parts. In addition, sometimes there can be interest in looking at the overall furnace in different zones. This can be used on a process basis, but also can be used for process optimization and tuning and balancing of the furnaces to get better overall performance of the part treatments. There's a number of self-diagnostics and other just monitoring aspects that the software can monitor and then report that via protocols to the plant so that operators get notified if there's any issues or concerns. And all of these things can be reported in different ways. There's standard protocols, and I list two at the very top here, Modbus and OPC, but many of these things can be also output in more traditional type IO, be analog outputs, relays, and so forth. So depending upon how these things want to talk to each other, there's different interfaces, protocols available. And finally, there's a lot of capabilities to also log this data over time, not just the data, but the actual video or the picture information. And this can be really important for troubleshooting. You can set up a system and be monitoring the key data that you need to know, but customers find value in also just saving the infrared images. Sometimes you don't know what you don't know yet. And so if something happens or some adjustment, maintenance, or some change in parts, um, if you've saved those infrared images, you can go back and look at how things have changed over time. And there's nothing like the eyes. When the eye is looking at the image, if as long as you save those images, you can see easily, slight changes in the process that maybe you aren't expected. So the ability to archive the infrared images and using software tools easily search through that archive and do analysis is another important function that these infrared camera systems provide. Just a little plug here for OPC communications. This is really becoming one of the most common protocols for sharing data in sort of the so-called industry 4.0 world that we're in now. And this is one that any infrared camera system you're considering should absolutely support. This is the way that different systems can share status, data, information amongst one another. So hopefully you know it, and within your industry you have, or within your company you have, automation people who work with this. And it's not the only protocol, but this is becoming kind of I would say the biggest in the space. And we got listed here some tags or kind of how data is shared between this. And we've talked about this a little bit already, but um, consider in any system that you're evaluating, what sort of protocols it supports, and within your own team, what expertise you have and who you need to get involved to really realize and close the loop in this value chain. Because ultimately, this is where the highest value comes when you've got really great sensors and you've got people looking at to figure out the process improvements, but really closing the loop is using protocols and platforms like OPC to kind of tie everything together and really automate these systems to bring the highest value to your operations. We want to share a case study of the use of the infrared cameras for furnaces. And this particular case study is a user who has annealing furnaces. And so before the integration of infrared cameras, there were thermocouples that were in the furnace, but just a few thermocouples, and they would try to put a couple witness thermocouples in the system to try to develop a batch process. But ultimately, once that was done, the process was kind of an egg timer technique, right? Based upon time, based upon those studies. And they had indications that this was not optimal. So they've invested in initially a single infrared camera to get an overview, and they kind of put it up in the corner of the furnace to see all the work pieces in the furnace. And after they integrated one, and based on the success of that, then they integrated it on all of their annealing furnaces. And we'll share a bit of the results on the next slide. What was interesting for this customer was a lot of their initial motivation was actually just confirming the part's temperature, but they got a lot more benefit than they expected, because what they found is once they were starting to accurately measure the part temperature, that they really were unnecessarily holding the parts at temperature longer than they needed. In essence, when they accurately measured the part temperature, not just the furnace temperature, they could see that the parts were reaching the process treatment temperature sooner than expected. And ultimately, they found that they were able to achieve about a 15% increase in throughput through the furnaces. And this was a huge savings to them in the long run, because they had, I think, 6 furnaces operating in more or less parallel. And taken collectively, it was almost like having a whole additional furnace, right? It was like having 7 furnaces. So it enabled them to defer expansion or investment in another furnace when they had that on the roadmap, and still maintain the quality, in fact, improve the quality, but improve also the tracing and traceability and tracking of all the part treatments. So better accuracy, better tracing, and with the improved capacity, a deferment or justification to not do further investments in overall capacity. It was a huge success, and we kind of demonstrated there in the time to temperature chart there, but just that, you basically, they can know with confidence that they're getting the right treatment and the right process done, but in a shorter time. And before that, there was just a lot of waste in capacity, and kind of waiting to make sure that all based upon just some thermocouples, that they thought everything was kind of up to temp, and then doing the treatment. So knowing specifically what was going on gave them the insight, the confidence, the precision knowledge that they could do accurate treatment and do it much faster, and save them a lot of money, and still giving their customers even greater confidence in the product. Thank you for attending and listening, or watching and viewing this presentation today. It's very interesting to do these events in this time we're in, these pandemic circumstances. So I really appreciate your attention and hope you learned something, and really would invite you to reach out to me if you have any questions or comments. You can see my email on the deck there. And again, my name is Lenny Shaver. I'm the Director of Products here for our thermal imaging systems at Advanced Energy. And I hope you're well. Take care, and look forward to hearing from you. Thank you.